There's a single patch of ground on Mars that NASA has decided to visit twice. That alone should stop you for a second. In more than 60 years of landing spacecraft on other worlds, we have almost never gone back to the same coordinates on purpose. Every lander, every rover, gets aimed at somewhere new, somewhere no camera has ever seen up close, because there's a whole planet out there, and returning to old ground looks like a waste of a rare and expensive shot. And yet, for one crater, the plan is to go back, to send a second machine to the exact spot where the first one already worked, already drilled, already left its tracks in the dust. The obvious question is why? Why spend years and billions of dollars to revisit a place we've already mapped down to the pebble? The answer is lying on the Martian surface right now, sealed inside a set of metal tubes about the size of a cigar, waiting in the cold for someone to come and pick it up. Here's what makes the decision so strange. When mission planners sit down to choose a landing site, almost every force in the room pushes them toward the unknown. Mars is bigger than most people picture. Its surface adds up to roughly the same area as all the dry land on Earth, every continent and desert and mountain range put together, with no oceans covering any of it. Drop a rover anywhere on that and you're studying a speck. So the instinct is always to spread the pins around the map, to touch fresh ground each time, to come home with something nobody has seen before. Choosing to send a second spacecraft to a place you've already picked clean cuts against all of it. It only makes sense if the first spacecraft left something behind on purpose, something that can't be collected any other way. And that is exactly what it did. The crater is called Jezero. The rover is Perseverance, which dropped onto the crater floor in February of 2021, lowered on cables from a rocket-powered platform during a descent the engineers only half-jokingly called the 7 Minutes of Terror. But Perseverance didn't travel all that way just to look around and send back postcards. It came to collect. Fixed inside its body is a system unlike anything carried to another planet before it. A compact factory of drills, bits, and sealed tubes built for a single job. Bore a finger-sized core out of solid Martian rock, slide it into a titanium tube, seal that tube against the outside world, and set it aside. Not to analyze in the moment, to keep. Perseverance is the first machine in history sent to another planet specifically to package up pieces of it and leave them ready for a journey home that hadn't even been built yet. Which lands us on a genuinely odd question. If you've crossed the entire solar system to reach a rock, why on Earth would you not simply study it there and then? To see why that question has such a strange answer, you have to go back to why Jezero was chosen in the first place. Because the crater was picked with the return trip already in mind. Seen from orbit, it isn't much to look at. A tired circle around 30 miles wide, its rim worn down, its floor the same rusty brown as everything else. But wind the clock back 3.5 billion years and that circle held a lake. A river ran in through a gap in the rim, slowed as it spread into standing water, and dropped everything it had been carrying into a broad fan of sediment. A delta. On Earth, deltas are among the finest natural traps we have for holding on to the delicate chemical traces of living things, because fine mud settles fast and locks them away before they can rot or scatter. If anything ever lived in that Martian lake, a delta is one of the likeliest places on the whole planet for a record of it to have survived the billions of years since. There was a second reason Jezero rose to the top of the list, and it's a subtle one. Orbiters had spotted carbonate minerals ringing parts of the crater. Carbonates form in water, and on Earth they are unusually good at capturing and preserving the shapes of ancient microbes, sometimes down to fine detail, for enormous stretches of time. A crater that was once a lake, fed by a river, lined in the very minerals best known for keeping biological records, is close to a jackpot for anyone hunting for signs of past life. So Jezero won out over dozens of rival sites, not because it offered the best view, because it offered the best odds of still holding an answer to the question we've carried to Mars from the very beginning. Was anything ever alive there? Before we get to what Perseverance found, it's worth understanding just how carefully those samples were handled. because that care is a clue to the whole plan. The tubes aren't simple containers. Each one was machined and cleaned to a standard closer to surgery than to plumbing, scrubbed of any stray Earth molecule that might later be mistaken for a Martian one. The rover carries more than 40 of them, and a handful were sealed empty on purpose. Those empty ones are witnesses. They ride along open to the Martian air at the drill site, catching any contamination floating around, so that when the real samples are studied one day, scientists can subtract whatever the witness tubes caught and trust that the rest came from Mars. You do not go to that much trouble for rocks you plan to glance at and forget. You do it for rocks you intend to defend in front of the entire scientific world, decades from now, where a single doubt about contamination could sink a discovery. Everything about the tubes says the same thing. These were always meant to come home. For a while, Perseverance kept turning up reasons to stay hopeful. As it ground across the crater floor and up onto the delta, its instruments began detecting organic molecules, the carbon-based compounds that form the raw scaffolding of life as we understand it. On their own, though, organics prove almost nothing. They turn up through plain chemistry in all sorts of dead places, in meteorites, in interstellar clouds, in spots where nothing has ever stirred. So the rover kept driving, kept sampling, looking for something with a stronger story to tell. Then, in the summer of 2024, it reached a pale reddish rock sitting in an ancient river channel, a rock the team named Cheyava Falls, then a towning Sums River. And this one didn't look like the others. Threaded across its face were off-white splotches, each ringed by a darker halo, patterns the scientists took to calling leopard spots. On Earth, markings shaped like that can be a leftover of microbial life, the chemical residue of tiny organisms feeding on minerals and changing the rock as they go. The same rock also carried thin veins of minerals that, on our own planet, often keep company with biology. Taken together, the mission described it, very carefully, as a possible sign of ancient life. Possible, not proven. And that one cautious word is the entire reason a second spacecraft has to make the trip. The trouble is that Perseverance, for all the genius packed into it, has run straight into the limit of what a rover can decide on its own. Working out whether a pattern in a rock was truly made by life and not faked by some patient trick of chemistry is one of the hardest judgments in all of science. Back on Earth, researchers reach that kind of verdict with instruments that fill whole laboratories. Electron microscopes that can resolve features finer than a wavelength of light, mass spectrometers that read the exact weights of atoms and tease apart the faint isotope signatures living things leave behind, because life tends to sort certain forms of carbon in a way dead chemistry usually doesn't. There are tests for chirality, for the strange fact that biology on Earth builds its molecules with a consistent handedness, all twisting the same direction, where lifeless chemistry scatters them evenly. None of that fits on a rover. Everything Perseverance carries had to squeeze onto a robot the size of a car, survive being flung across more than 100 million miles of vacuum, and then get dropped intact onto a planet that swallows half the missions sent to it. The rover can catch the hint. It can point at the rock and say, "Look here." It simply can't hand down the final ruling. That ruling only comes from the machines back on Earth, and those machines are never going to Mars. So if the answer can't travel to the equipment as a radio signal, the rock itself has to travel to the equipment. There's no other road to certainty. You might wonder whether any of this is necessary, given that we already own pieces of Mars. We do. Every so often an asteroid slams into the Martian surface and flings chunks of rock into space, and a few of them drift across the solar system and fall to Earth as meteorites, where scientists have collected and studied them for years. So why go to all this trouble for more? Because those meteorites arrive with no address. We don't know which region they came from, which layer of ground they belong to, how old their surroundings were, or what the land around them looked like when they formed. A rock stripped of its context can answer plenty of smaller questions, yet it falls apart on the big one, because a whisper of possible life means very little if you can't say where on the planet it appeared or what was happening around it at the time. Perseverance's tubes are the first fragments of Mars that come with a full history attached. We know the crater, the layer, the exact rock each core was cut from, and everything the rover watched happen nearby. That context is what turns a curious sample into real evidence. At this point, another fair question shows up. If the whole problem is that our best instruments are stuck on Earth, why not just send people, scientists who could study the rock on the spot, or at least gather it far faster than a robot creeping along at a walking pace? The honest answer is that we're nowhere near ready. A crewed trip to Mars means keeping human beings alive through months in deep space, shielding them from radiation the whole way, landing far more mass than we've ever set down on that surface, and then launching them off it again. It would cost many times what a robotic return costs, and carry a level of risk we don't yet know how to accept. There's a quieter reason too. People are messy. We shed skin, bacteria, and water vapor with every breath, and dragging all of that into the one place we're trying to search for native Martian life is close to the worst thing you could do to the evidence. For this particular job, a careful robot that touches almost nothing is the better scientist. So the sample comes home first, and the astronauts, if they ever come, follow later. Which brings us to the part where a science story turns into something closer to an engineering nightmare. Lifting a sample off the surface of Mars and carrying it home is, by a long stretch, the most complicated robotic mission anyone has ever tried to design. Walk through what it actually demands. First, a new spacecraft has to land close to where those tubes are waiting, softly, inside the same crater, hitting a mark on another planet with enough accuracy to matter. Landing on Mars is savage even once. The air is thin enough that parachutes barely grip, yet thick enough to heat a shield to a glow on the way down. A craft screaming in from space has only a few minutes to shed thousands of miles per hour and settle onto the dirt, with no chance for a human to reach in and correct it, because a radio signal takes so long to cross the gap that by the time we'd see a problem, the spacecraft would already be wreckage or safe. Somewhere close to half of every mission ever aimed at the Martian surface has ended as a crater or a silence. This one would have to come down gently on a chosen patch of ground, right beside hardware already sitting there. Then comes the step that has genuinely never been attempted. Once the tubes are aboard, they have to leave the planet. A small rocket has to stand upright on the surface of Mars and fire itself into orbit, with the samples tucked inside. Nothing built by human hands has ever launched from the surface of another planet. Not one time in the entire history of spaceflight, every rocket that has ever climbed toward space lifted off from Earth, from a pad we built, watched over by people who could scrub the count the instant something looked wrong. This one would rise from red ground tens of millions of miles away, with no tower and no one nearby to help, lighting itself and leaping into a pink Martian sky on the first and only try it gets. If it tips, if it stalls, if the cold of the Martian night has done something unexpected to its fuel, there is no recovery. The rocket has to work, alone, the moment it's told to. Even clearing the atmosphere isn't the end of it. That rocket only lifts the samples into orbit around Mars, where they'd be let go as a sealed container roughly the size of a basketball, tumbling slowly against the stars. Another spacecraft, already parked in that orbit and waiting, would then have to track the container down, close in, and catch it. And here the caution reaches almost paranoid levels, for a reason worth knowing. Anything we bring back from Mars is treated as though it might, however unlikely, carry something that could harm life on Earth. So the container would be sealed inside layer after layer of containment, wrapped so completely that not a single grain of Martian dust could ever leak into our own world, before the spacecraft turns and begins the long, quiet fall toward home. Most scientists think the odds of any real danger are vanishingly small. They plan for it anyway, with the seriousness of a laboratory handling the deadliest germs on Earth, because you only get to be wrong about this once. Every one of those handoffs has to work in sequence, a relay stretched across more than 100 million miles, where fumbling the baton even a single time means losing all of it for good. There's one detail in this whole plan that tells you how seriously the people behind it take the danger of failure. Before Perseverance carried its main collection anywhere, it paused in a flat stretch of the crater the team named Three Forks, and carefully set 10 sealed tubes down onto the surface, one at a time, laid out in a deliberate pattern so they could be found again. Now we showed a backup. A second copy of the samples, left out in the open in case the rover itself breaks down before it can hand its cargo over. So there are now, in a real and literal sense, tubes of Mars resting on the surface of Mars, arranged and waiting, like a message left behind for whoever manages to return for it. It's the first supply depot our species has ever staged on the ground of another world, put there for a rescue party that hasn't launched yet. That backup plan has an unlikely hero behind it. Perseverance carried a passenger to Mars, a helicopter barely bigger than a tissue box called Ingenuity, meant only as a short experiment to see whether powered flight was even possible in air 100 times thinner than ours. It was supposed to manage 5 flights. It flew dozens more than that, over about 3 years, scouting the ground from above long after anyone expected it to quit. And its stubborn success quietly reshaped the retrieval plan itself. Once engineers watched those little rotors bite into the Martian air and fly again and again, they began folding small recovery helicopters into the design, as a way to fetch the waiting tubes off the ground if the rover somehow couldn't deliver them. A throwaway science toy ended up rewriting how we might carry the most valuable rocks in the solar system to safety. So the plan is hard. It is also, at this moment, unsettled, and that part is worth being honest about. Bringing the samples home was meant to be the triumphant next chapter, the payoff that justified everything Perseverance was sent to Jezero to do. But as engineers filled in the details, the cost and the timeline kept swelling, until independent reviewers looked at the figures and said plainly that the plan as drawn couldn't work, that on its current road the samples might not reach Earth until somewhere near 2040, at a price running well into the billions of dollars, pretending the duo IDs. So the agency hit pause. Rather than march ahead with something it couldn't pay for, it stepped back and asked a blunt question. Is there a cheaper, faster way to lift a rock off Mars? More than one option is now on the table, and no single road has been locked in, which leaves the whole effort in a peculiar place. The samples are already gathered. The tubes are already filled and sealed. The single hardest scientific act in any sample return, getting the right pieces of rock into the right containers out on the surface, is finished and behind us, and those containers are just sitting there in the freezing dust, while back on Earth we work out whether, and how, we can afford to go and collect them. It's worth stopping to picture what actually happens if we do. One day, if everything holds, a sealed capsule falls through Earth's atmosphere and settles onto a stretch of desert, and inside it are pieces of another planet that no living thing has ever touched. They'd be carried into a laboratory built like a fortress, sealed away behind glass and glove and filtered air, opened under conditions cleaner than an operating theater, and slid, at last, under those room-sized machines that Perseverance could only dream of. Then the real work would begin. Teams that had waited most of their working lives for this would take their turns, running the same speck of rock past instrument after instrument, checking each other, arguing over every reading, refusing to say the word until the evidence left no room to say anything else. And on that first morning, a scientist somewhere would read out the very first measurement of whether a Martian rock carries the fingerprint of life. That single moment is the target of this entire, absurd 100-million-mile relay. Everything else is just the effort to make it possible. Because think about what's riding on that reading. If even one of those tubes holds solid evidence that something once lived in Jezero's vanished lake, it would stand as the most important discovery our species has ever made. That isn't a figure of speech. It would be the first proof that life began somewhere other than Earth. It would mean that on 2 separate worlds in one unremarkable solar system, plain matter found its way into being alive, and if it happened twice in a space this small, it becomes very hard to believe it didn't happen over and over across a galaxy holding hundreds of billions of stars. Overnight, the universe would shift in our minds from a place where we might be the only ones to a place that quietly grows life wherever the water and the warmth line up. And there's a twist most people skip past. Even the letdown answer would be staggering. Say the rocks come back, the laboratories run every test they have, and they find nothing living, only chemistry that happened to imitate the look of it. That result would be enormous in its own right. It would tell us that a young planet with rivers, lakes, and every ingredient we think life needs can sit there for hundreds of millions of years and never once cross the threshold into biology. It would mean the spark is far rarer, far more fragile than we've let ourselves assume, which says something heavy about how alone we might really be out here. Whichever way it breaks, the answer rewrites the story we tell about ourselves. And that answer isn't waiting in a textbook or a simulation running on somebody's laptop. It's waiting in a tube, in a crater, on Mars. There's a human weight to the delay, as well. Some of the scientists who gave their careers to these samples first argued for bringing Mars home decades ago. A few of them may well retire, and some may not be here at all, by the time those tubes finally reach a clean room bench and the seals are broken. They gathered the evidence for a discovery they might never personally get to read. That's the quiet gamble underneath all of it. We reached out across the solar system, closed our hand around what could be the answer to whether we're alone, and then set it down and started arguing about the trip back. So there's one spot on Mars that we keep returning to, in our plans and in our imagination, a crater that was a living lake while the Earth was still learning how to hold life of its own. Somewhere on its floor right now, a handful of small metal tubes sit sealed in the dark, holding what might be the oldest answer we've ever chased. We've already gone out and picked it up. The only thing standing between us and the truth is the journey home, and whatever is locked inside that metal has kept its silence for 3.5 billion years. It can hold it a little longer, while we find the nerve, and the money, to go back to the same spot on Mars, one final time, and carry it the rest of the way.